Yeah, I want to proceed with the homothety thing because actually homothety is one of quite large, it's substantial, and like which you may meet in very different situations topics. And we just touched it superficially last time. Just 1 second. Our notebook. Okay. Uh, First of all, I want to ask you guys, like, um, who did the problem with those 3 points on one line? Like, did somebody succeed? Like, I saw something you sent to me, but I want to be sure because sometimes you send not all the solutions. Um, like, I mean, not you precisely, but like some students solve something but send less than they solve. So if you did it, please let me know in like by raising a hand or write into chat, anything. Um, but actually, like I want to start from a slightly different application of homothety. Maybe even more classical because that problem with 3 points on one line, that would be already applying composition of three homotheties. While even one homothety may give a highlight on several quite complicated otherwise situations. So for example, if we have a combination of touching circles, that would be one of the basic examples how a homothety may be used. So, for example, let us have this situation. So it turns out that these 3 points would be collinear. So T X, Y. Here, A and B are supposed to be parallel. Uh, Two circles touch externally each other, and uh, the parallel lines A and B as on the picture prove that touching point X, Y, and T are collinear or belong to the same straight line. Are there those who are familiar with this problem? Who knows this problem? No one? Okay. Then let's start from several minutes of thinking about this problem. So do your best to have some progress in the problem and in some 5-10 minutes, we will discuss it. And before that, I'll just put more classical examples of homophety here. Just in case, take a screenshot, please, of this. Maybe I'll be flipping the page. Потому что я дал задание, и сейчас я кое-что делаю еще. А что такое? Водички хотела? Камеру не влазь, пожалуйста. Так вот открыт.
Нет, нет.
Дальше.
Папа, я смотрю, закрою.
Мгм. Потом тебе расскажу. Okay. Um, let's move to the discussion, maybe in half a minute or a minute. Just if you had some ideas, please send me on WhatsApp, so that we can like I can see them before, like I can see them without interrupting them. Oh, кадр не заходи, кадр не заходи, пожалуйста. Я не знаю, в шкафу где-то. Ты хочешь эту бутылочку? Сейчас смотришь, я через пару минут смогу подойти. Возьми-ка пока синий стаканчик, пожалуйста. Он рядом с белыми чашками. Окей. Okay. So seems like I I saw what you at least started writing to me. Somebody answered, like gave the complete answer, more or less. So yeah, the idea here is that there are several standard things, several standard maybe tricks, so that we know that we may start from them, and then we most likely will have some guaranteed results. So here, what is very probable to be used would be homothety with the center T. Just 1 second, sorry, one minute more. So there are some signs that we better do the homothety with this center. For example, an auxiliary exercise may be done that if two circles are touching each other, then there exists a unique homothety which sends no, it's not very correct. Like there is a homothety with the center T. There exists homothety with the center T such that sends omega 1 to omega 2, where omega 1 and omega 2 externally touch each other. So I call such statements structural exercises because they're not that difficult to be called problem. So it's very straightforward in some sense. So we denote here omega 1 with radius 1, here omega 2 with the radius 2. We may even introduce some coordinate system or whatever and like put T to the origin, and then we just do basically anything so that we can prove by the definition that it's doable. So here we may notice different things like the centers and the touching point should be inline. So like we can literally describe how do we send this center to that center, then prove that the circles will follow. So I advise you to do this exercise completely so that you understand the details. So what is known now? So there exists homothety with the center T and some coefficient. Which we denote just H, so that H of, we call this omega X, this omega Y. Малыш, ты сейчас, пожалуйста, не надо со мной разговаривать, потому что я сейчас занят. So we know that homothety of omega X is omega Y. And that's basically it when we define the homothety. And what's next then? So not that much done at the moment, right? But what we can do, like today I was like few moments ago I was educated a bit more. Like I studied what is phantom point. Like I never knew that the method which we used like in our Russian trainings is called phantom point. Though it's quite clear by the concept. So here we sort of use phantom object. So what we'll do now, we'll do following. We'll take the homothency, which we just defined, and we consider the images of like everything related to omega x with respect to this homothency. So we know that this circle here goes here, and the line, the straight line B, it will go to some position. Sorry. So we have sort of phantom straight line. But what do we know next then? So we have here straight line B prime. So let B prime be a result of homothency applied to the straight line B. Then we have several basic properties. So B prime is parallel to B, first of all, right? And which is parallel to A. And also, like, so we have here that B prime is parallel to A by transitivity of parallelism for straight lines. And also we have that B prime is tangent to omega y. Why is that? As B is tangent to omega x, and homothency preserves intersections and touchings. So this part I don't explain again, like this quite important note. Maybe just some images to imagine. Like it follows mostly from set theoretical properties of the situation. So if we had a pre-image of some object, and this is related, like this property is deeply related to the fact that if we have non-degenerate, like well-defined homothency, then always there exists the inverse homothency, such homothency which brings everything back. So that is another important exercise. Да, здорово. Да, медуза точно. Сейчас мы вообще... So, for any homothency with center x and coefficient k, where k is not equal to 0, there exists h to the minus first, like the inverse homothency, where like maybe this is not very best way to denote it, because this is supposed to be not the coefficient, but this is supposed to be the minus first power of h. So maybe it's better to Okay, let it be just t, and I will write down the fact that it's inverse just in words. So there exists t such that t applied to this equals to id, and also in the inverse order it's also id. What does it mean technically? That means that there is some homothety, which, like, for example, here we have a homothety. We do it, and the inverse homothety applied after, it will just inverse all the process. So we again will have omega 1, omega 2, no, how it goes. Like after the first homothety, omega 1 goes to omega 2, but the second homothety will bring back omega 2 to omega 1, and vice versa. Like for any particular point, it would be sent somewhere by the first homothety and sent back by the second homothety to the preimage. And this homothety would be very trivial. It would be just homothety with the same center and point x and coefficient minus k, not minus k, but 1 over k. Just a sec. Юруш, не надо туда наливать. Яри, зачем? Зачем ты туда наливаешь? Нет, оттуда не надо пить, пожалуйста. Вот у тебя есть чашечка, у тебя есть стаканчик. Пей оттуда, пожалуйста, Ируш. Отсюда пока что не надо. Потом, когда мама придет, когда мама сможет с тобой рядом постоять, посмотреть, тогда вместе с мамой ты сделаешь. Okay. So, what does it mean here? It actually, like, we use it all the time to show that if two objects had, say, 2 or 3 or k points of intersection, then after a homothety, they will have exactly the same amount of points of intersection. That is, of course, more specific to finite amount of points in intersection, including the case of no intersection at all, right? And why is that? Just because if we have exercise 3, two objects have no intersection, and we send them with the homothety to some two other objects. So, for example, here, suppose we have homothety with negative coefficient, like negative 1 second, for example. How will it look like? Like it will be looking like this, more or less, like in this center. So for every point, we draw this vector through the center of homothety, HC and -1 second. So this is just for the example, right? So it sends this to approximately this. Another thing it will send somewhere over here. Also 2 times less, speaking of one-dimensional parameters. Any length, any width would be less by half. And they wouldn't have intersections. So like it would be rather something like this. So if two figures had no intersection, then after applying a homothency, their images will also have no intersections. Why is that? That is because this is not very direct thing. So if they had, imagine first that they had 2 points of intersection in the beginning. Then after taking the homothency, we can track where those 2 points go. And we can say, okay, these 2 points, they still belong, like not these, but the images of these 2 points, they belong to the images of the both figures. Like it was part of figure 1, like point X, for example, was part of figure 1. So we draw another thing for that. So if they had something, and after sending, after making the homothency, we had these points A, B. Here would be like A prime. So these are exercises or properties as well. Like more importantly, they are properties which are often or frequently used, but on some very, very fundamental level of explaining. So suppose two figures had k points of intersection before then their images at the homothency will have the same amount of intersections. So now imagine we take 1 point of these. So again, here is the center, C. So we can literally track where it goes, right? It goes to here. And we can say that A prime would be still part of the image of figure 1. It would be part of the image of the figure 2. So it definitely will be part of the intersection of the images. So any intersection point will go to intersection point. But suppose that there are some extra points of intersection. Then we will get use of this exercise too. We can take then the inverse homothency, which brings every of the images to their pre-images, so which reverses the transformation. Then any extra point of intersection must go to an intersection point of the pre-images. So if there would be X prime intersection point, it must go to an intersection of the pre-images, which are just initial figures. That means that any, I would say, new intersection of the images, they must have some pre-image in the first homothéty because the image in the inverse homothéty would be just literally the same point. So that is how we show that there is one-to-one correspondence between the intersection points. But here, in this citation, in the previous citation, we may now prove it by the same method, by proving by contradiction. So the problem here is that we speak of something which doesn't exist. So according to what we discussed in the first classes, in the first lectures, it's hard to discuss something which not exists, right? We cannot study the properties of such object because we don't have the object. But what we do would be this virtualization. Like we imagine that it exists, and if it existed, it would have the following properties. And here, like we have this classical implementation. So imagine that images of these two not intersecting objects still will have an intersection. But then we have the inverse homothéty, which must bring the intersection point to an intersection point. And that intersection point must be intersection point of the images of the images, which by the coincidence, actually by the choice of the second homothéty would be just the initial figures. So if we have an intersection of the images, we must have had intersection of the pre-images of the initial figures. Okay. So here now we have this, that we had the tangent line, we had the circle. So the images will be a circle and a tangent line. So that is why I write here that B prime is tangent to omega y. Okay. But then we have that. So B prime is tangent to omega y as A, and B prime has the same direction as A. So speaking inaccurately, we already may notice that probably B prime then coincides with A because we have straight line which is parallel to A and still tangent to the circle. So for example, they would have they must have parallel radii to the tangent point, right? So if we draw this radius for the first line, if we draw the radius for the second line, they are perpendicular to parallel directions, so they must be parallel to each other. So that actually says that either they will coincide or they will be two opposite vectors if we imagine them as vectors. And actually that is what pushes us to the idea like that we must show that B prime cannot be the tangent line from the opposite side. But this is more combinatorial question. So here I will probably skip this part. Because yes, like with this homothéty, we can say that the coefficient of the homothéty must be negative, so that the direction of a vector, which any vector which we consider, it must change to the opposite. So any vector goes to a parallel vector, but with negative coefficient, it apparently goes to the parallel vector of opposite direction. So here, that means that if we introduce some system of coordinates with axis x here, y here, so that we can discuss this in the terms higher, lower, to the right, to the left. So we then can say that if we take omega x as the lower circle, then, or like we take the line B as the lower line, then the tangent, the radius of this circle directed from the center to the tangent point would be looking downwards from positive from greater numbers to lower numbers. If speaking of the y-axis, let's redraw it. And then that means that after homothety, the image of this radius, so the radius here will be this, it will be sent to direction which is going from lower numbers to to larger numbers, and that is how we can derive that A and B prime should be on the same side of the omega y. But this is supposed to be just tiny part of the logic of the proof. So I don't like to do such specific, to specify in these details when we discuss this orally, because oftentimes such small details they take more our attention than they sort of deserve. So we still must do them. We must do them accurately and precisely. But the very sense of the problem would be this geometrical twist with homothety, while the time which we will spend on the trick itself and the time which we spend on the on these like special cases or special adjustments, like they may be slightly incomparable. So finishing the proof. Now we have A coincides with B prime. They coincide. So here, actually, some part of explanation, it was pronounced orally by me. On a competition, you don't forget that sometimes it's not clear which exactly details you want to put like for the explanation in some trivial place. So you better at least give a hint to the reader. What did you mean? I would say in the oral part. So normally I would give more details over here. But that is also sort of, but like this would be already a bit more difficult to use as a preliminary prepared exercise. So we have more general statements here, but for the circles, we may formulate a similar thing, but sometimes we just need a bit more, right? So we needed here special position of the straight line as well. So here we have that finally A equals to B prime. So that is why it was phantom position of the object. And now we can deduce from here. So Y is B prime touching the point where B1 is touching omega Y, right? So even not omega Y, but omega X prime, which is omega Y. So that is how we show that actually Y is the image of the homothency of X, right? But if it's image of the homothency, then by definition, the pre-image, the image, and the touching point, they must be inlined, or they must be collinear. Like this. Any questions?
Yes. Would
Yep.
the solution I sent you be enough in a contest, or will I have to specify more?
Just 1 second. Uh, like, I will. It's Karim, right?
Yes.
Like I will give you a bit more specific comments, like personal comments, in the chat. Speaking of the exact what you wrote, but I will use as this as an opportunity to give a general comment on like the methods which we apply. So you should always account not just for the simplicity or complexity of the method itself, but also the simplicity or complexity of the or difficulty of the problem which you solve. So if you use a method which is, I would say, same complexity and difficulty as the problem, and it's even not clear what is more simple, the problem or the method, and the method is not very standard, at least to you. And you don't like, then you probably should provide more details. Even if you know that somebody knows this method is very standard. Oftentimes here some play happens, some game happens. You try using some complex method, but underestimate some particular cases or just misuse some small things or like whatever. And in such situation, if no additional details were provided, the problem would be normally graded as 0 points. Just because no details, some issue with the standard method or like close to standard, and like no chances to give some intermediate points, right? But if it would be some bigger problem, and the method which you use would be like a small thing comparable to the entire problem, then even if you do the same range mistake as in the previous situation, namely, if you do even the same mistake as in a simple problem, this may lead to a smaller deduction of points, just because it's some small part of the problem. You found the correct method to deal with that part of the problem. You just made some like internal mistake at that spot, at that part of the problem, but still it preserves the opportunity to come back to that part of the problem and sort of refine the solution, do it better, maybe even apply something different. So structurally, you did correct division into parts, and you definitely made an advance comparing to like doing nothing. So from this point of view, if you have like having a simple problem and mistake in a simple problem is something which is worse than doing a mistake in difficult problem, at least speaking of competitions. That also accounts for not just mistakes, but some gaps in explanation. So if you see that the method which you want to apply would be of comparable complexity to the problem which you want to explain in that way, then you probably should give more details, because sometimes you will find out that the problem would be sort of relative problem to the method. It happens sometimes. And like if from the point of view of the grading person, your methods potentially have the same gap in explanation, at least in your understanding, that some solutions of that problem have gaps on that exact competition, unexpectedly that may lead to decrease of points. So in a sense, that means that with simple problems, you must do sort of longer solutions than for the complex problems. That was like general comment, not addressed exactly to Karim's answer. It's just like to Karim's solution. Just it reminded me this topic because, like, as a grading person, as somebody who grades solutions on Olympiads, I oftentimes meet this issue. And when we apply some methods like homotheity, and we write something like, we just apply homotheity with these centers and with this center and this coefficient, and that's it. That may lead to troubles on a competition. Okay.
Okay, thanks.
You're welcome. But like that wasn't addressed answer to what you wrote. Like I will write some more personal. Okay, let's shift then to some new let's have a couple minutes break. I will take my coffee and you have some rest from me speaking. You can actually have a look at some new problems meanwhile. So here we have two touching circles and the tangent line to one of them. What we should prove is that the straight line passing through these two tangency points, it must pass through the midpoint of the arc. And here in this situation, we have in circle, we have out circle. We then, the easy part is to prove that the centers lie on the same, the centers and the vertex, they lie on the same straight line, but this is quite famous even without any homothety. But where homothety is useful is that the tangency point of the X circle with this side of the triangle and the point which is how it's called, diametrically opposite to the touching point of the in circle and the same side. These 2 points and the vertex are also collinear, belong to the same straight line. And now, we have a break, around 5 minutes. 1, 2, 3. Can you hear me well?
Yes, we can hear you.
Okay. Okay then. So this would be two problems from your home task, but that would be not what I want to discuss in much details now. Now I want to actually to move forward and to speak about composition of homotheties. By the way, I can give you an example of no, that would be a spoiler. Okay, composition of homotheties. So when we speak of composition, that basically means that we apply one after another, right? So if we consider two homotheties, what will happen then? So we take one center, no, let it be X and Y. We take homothetity homothetity with center X, coefficient K1. No, let it be not K1, let it be P. And here homothetity with center Y and coefficient Q. Like, what may be this thing? What we know, so let H equal to homothetity, say this first, and then this applied. What I didn't mention about homothety, which is actually considered one of the very primary properties, is that homothety, non-degenerate homothety, homothety with K not equal to 0 is a similarity transformation with similarity coefficient K. Like absolute magnitude of K. Because K may be negative here, but when we consider similarity, we normally consider the ratio of two lengths, which is always positive, so it must be positive. What is similarity transformation? Basically, by definition, similarity transformation means that a any A and B go to A prime, B prime, so that length AB, A prime, B prime equals to K times length AB. Here, probably more correct would be taking this magnitude lines, vertical lines, to the K as well. Here they are used for A prime, B prime, and AB, just to show that that is length of the segment, not any other parameter, not the vector corresponding to that segment, like nothing but just length of this. And K here would be, of course, then supposed to be positive. But we already use it somehow here, so I recommend that for your just understanding. So this is definition of similarity. But this is just formal definition. Informal definition is the very fundamental property of similarity, which means that for any triangle ABC, it is sent to A prime, B prime, C prime, so that first of all, they are similar. And coefficient of similarity is exactly K. So here with coefficient K. So that basically means that if we had any triangle, then like we don't know much about orientation of the triangle. Like the transformation may be constructed in some strange way. But if we know that that is similarity, then we automatically know that we must expect this similarity of triangles. So here we have small words play, right? Similarity of triangles and just similarity, while they are understood as different terms. So similarity is supposed to be transformation of plane, and similarity of triangles is a relation between two triangles. But somehow that works well. Probably that's why we still use it, almost with no confusion. So homothety, one of the primary properties is that homothety is a similarity, and that is quite straightforward. Why is that straightforward? You can check, but for example, for the segments which, if we take one of these 2 points, the center of homothety, that would be just sort of part of definition, right? We know that segment OA or segment OB, for example, it goes to a segment OB prime, so that the vector OB prime is equal to K times OB, where K is the coefficient of homothety. Then, of course, the lengths of these segments, they would be related by exactly this equality, that would be straightforward. But for two arbitrary points where no center is involved, we actually will have very similar thing, like by basic similarity properties for triangles, we will find this as well. So when we come back to composition of homotheties, we then know that for any 2 points A and B, A goes to A prime with the first homothetty and goes to A2 primes with the second homothetty. Same story to B. So A prime, B prime equals magnitude of P times length of AB, and A double prime, B double prime equals same thing for A prime, B prime, and coefficient Q. So we have that A prime, A double prime, B double prime, the overall image, it's related to the pre-image in this way. So actually, by the definition, so it's similarity transformation. And it already means that we will have all those similarities of triangles. So here we have AB, A prime, B prime, A double prime, B double prime. And that is how it works. So that is first thing. Second thing is that if we want to realize that H is homothety itself, and that would be the case actually in most of the situations, then we must have the center of homothety, right? Like there cannot be any homothety without its center because it's like one of the basic defining structures.
I have a small question.
Yep.
Does that mean that for every two similar triangles, there is some homothety between them?
Sort of, yes, but with some limitations. So if we speak of just homotheties, we will soon speak of rotational homothety, which is even more powerful. But if we speak of just homotheties, actually my drawing here is not very accurate. It's already about rotational homothety more. So here it would be rather this. So we have with homotheties we have we have parallel lines all the time, right? And if the two similar triangles would be with parallel pairwise parallel lines, then it is almost true with one exception. So if we have any two triangles with parallel lines, they would be there would be homothéty existing if they are not translationally equivalent. That is called translationally equivalent. That means that if they are not, how to explain that in the shortest way. So the only exception is if these two triangles, is if one of these two triangles can be obtained from another one by a translation, by a parallel translation. So that would be the only exception, because technically we will have technically the center of homothéty, if we try to start constructing it geometrically, it will just run to infinity and it will give us no real point. But also, supposing that the homothéty point is homothéty center is in infinity, will also not work there. So we just say that it's clear exception. But otherwise, in any other situation, so for example, they are congruent but not translationally equivalent, like one of them is rotated 180 degrees, or they are just having different size. If they have different sizes, then no exceptions. They just have a homothéty center all the time. Let's have the diagram. So if we take homothéty with this center, which brings this point to this point, and this point to this point, and also the internal side of the triangle to this internal side of the triangle, then the position of this point, the position of this point, would be defined exactly as the image of this point under this homothéty. Because even if we bring this segment to this segment, there are two options actually. We also may try other order of the point. So this goes to this and this goes to this, which also suggests a different position of the center, but that would be corresponding different choice of the internal side, right? So if the triangle would be flipped to this side over this segment, we must have a different order of correspondence of the vertices. But if we realized in which order we must do that, then for different sizes of the triangles and parallel position of the sides, we always have the homothéty. So that is correct. And here, speaking of the composition, we then have that actually there is an expected, I would say, attention area where the center may arise. So basically, it's more or less intuitively clear that the center of this homothéty, if it exists, it must exist somewhere over this, along this straight line, along this center line. And that is actually true. How to realize that? Let me just keep it as as an exercise so that I don't recall it. Just keep in mind that if we have case when p times q equals to 1, which makes this coefficient equal to 1, We may have this exception situation when triangles, the initial position and the end position of the triangle, they are not homothetical to each other, even though they may be obtained by composition of two homotheties. So if they have equal size and they are oriented equally, so that is this situation. Sorry. So we have two congruent triangles. Oriented equally. Then if we try to perform this construction, we will have just family of three parallel lines, right? So they cannot be related in similar way. But this situation may arise as the result of this construction, just if P times Q equals to 1. That will result in the triangle with double primes having the same size as this. And if there is no constant point, then everything will be shifted. So it will depend just on the fact if there exists one constant point or no such point. So try finding this center. So center. Of course, I will write it again like as home problem. And there actually follows the theorem that composition of two position of two homotheties is always a homothety, but besides one particular case when K1 times K2 equals to 1. And some point x, actually any some point x has its image x double prime not equal to x. So in this situation, if we take some point and we find out that its image is not coinciding with this point, then we have that for any other point, it will be the same situation. And with this specific property that the product of coefficients equal to 1, that means that there will be no homothety. If the product is 1 and x double prime coincides with x, actually again for at least one point. Actually, that means that we may take any point as the center of homothety because it would be just identity transformation. No changes at all. And for any other situation, when the product of coefficients is not equal to 1, then it would be just true homothety. The coefficient of the resulting homothency. Homothency is equal to K1 times K2. So this is the important theorem, which may be already used for proving that theorem about 3 points on one straight line. But what I wanted to mention today as well is rotational homothency, which is somehow related to these questions, but also involves rotation as its part. So first of all, sorry guys, that much information today, like much new information, I believe, at least partly. Many definitions. So the question for now, who knows and who dealt with a rotation as transformation of plane? So I bet you all know that rotations are related to geometry, to plane geometry, but who dealt with them as transformations, plane transformations? Okay, I see now one comment in chat that it was something like related to polar and cylindrical coordinates, and that is strong yes, that rotations would be deeply related to these things, to polar and cylindrical coordinates. By plane transformation, I mean mainly like a topic of plane transformation. So I wonder if you had such topic anywhere. Basically, that means that you had some like specially formulated sort of definition of a rotation as a procedure. So you can speak of rotations intuitively, that look, this triangle is rotated respectively that triangle, and that's it. But you may consider that as some standard procedure defined uniformly. You can even have some standard notation for that. And if you just had such lessons, such topics, then I understand that you most likely know some particular consequences, consequent facts. So I will then mention that briefly, and then that would be just a joint topic of transformations of plane, including all these things like homothencies, rotations, rotational homothencies. So if we have a rotation, rotations, my rotation with center C, a point which is called center of the rotation, and phi is angle of the rotation. So if we have any point A, then the image of this point would be point A prime, such that some very natural things will be fulfilled, natural conditions. So we must have that the rotation counterclockwise would be performed by the angle phi, and the radius vector, not the radius vectors, but these radius segments would be equal, such that the directed angle AC A prime equals to phi directed and counterclockwise. And the segments CA and CA prime are equal to each other. So these would be rotations. Any rotation is exercise something. Any rotation is congruency transformation. That means for any A, B, the images A prime and B prime are such that the length of AB equals to the length of A prime B prime. And this is quite a huge thing, because that means that any triangle will be preserved, even degenerate triangle. If we have 3 points on a line, they will go to 3 points in a line with the same preserved distances. And that basically means that all we consider within one rotation is moved as a firm body. So that is very physical interpretation. So if something is moved in the context of rotation, so triangle, for example, moves with the rotation, then all the internal objects of that triangle, like medians, bisectors, like angle bisectors, orthogonal bisectors of the segments, any other structures defined intrinsically, like by the internal terms of a triangle, they move as a firm body. They move together with this rotation. And there would be a theorem that composition of two rotations. Oh, sorry. Composition of two rotations is a rotation besides probably the case when P1 plus P2 will be here equals to 0. If Phi1 plus Phi2 equals to 0, then it may be also an identity transformation. So this, as you may notice, looks very similar to what we had for the homotheties. How it would be proved? It would be proved both in slightly, like in a similar, but also in a different manner. We will be keeping track of some other parameter. So we know that for transformation, we have this segment, the sizes, the lengths of the segments being preserved, which is very, very powerful property. But still we have, if we have two rotations, then we have something like this. So we have, say it's X, it's Y, as we introduced it initially. And for example, here we had point A. So the point A goes here first to A prime. Then it goes further over here as A double prime. And point here, B, it goes somewhere over here. So it's B prime. And over here it goes then somewhere over here, B double prime. So you can notice that it's not that easy to, though the length of the segment would be preserved on every step, because like I say every step because like we further will consider composition of 3 and probably even more rotations, normally 3. So we know that the length of the segment will be constant on each stage, but still observing the trajectory looks a bit troublesome, I would say. So what will help us actually considering the direction of the vector. So lemma, which would be probably, we will see if I keep it for your home task, would be that the direction of a vector of any vector A, B is rotated by exactly phi under a rotation with angle phi. So speaking, I don't know, intuitively, it sounds like a very reasonable thing. Like we have rotation by phi, so probably the direction will be also rotated by phi. But actually, as to me, this is one of most non-trivial parts of all the topic of transformation, like congruency transformations and a combination of transformation, because the angle here and the angle here, they are considered in completely different positions, in completely different places of the plane. So here, probably we will discuss it now. So imagine we have a segment, a vector AB over here. So it is AB. This is the direction of the vector. Here is the center C of the rotation. And we have this rotation somewhere. I will draw it, sorry, as a clockwise rotation, but that's okay because we may have any angle phi as the rotation. So it may be, for example, 270 degrees, which technically could be replaced with -90 or any other angle, which is like, which would be reasonably to consider as the negative rotation, right? So we have this thing, more or less. So this would be A prime. This would be B prime. This would be the direction of the vector A prime, B prime. So what is claimed is that the direction of this vector is rotated to this direction by exactly angle phi. Oh, sorry, phi is not here. Phi is here. But the question is, what is a direction of the vector then? So by a direction of the vector, we may consider just like we do in many situations with vectors, just the representative of the same vector, which would be placed so that the start point of the vector is in the origin. So the rotation center is not necessarily in the origin. And actually there is no necessity to to compare the directions exactly in the origin, in the initial point. But it's the most natural way to do that. So we can just do a parallel translation of this vector AB to the origin and of A prime B prime. So this would be AO BO. And here would be A prime O B prime O, where AB equals to AO BO as vectors. sorry. A prime B prime is equal to A O prime B O prime. And all the starting points here, like AO equals to AO prime equals to O. So we literally just do translation of this vector to some fixed point origin, preferably, and this vector also to the same point. So the statement here is that the sense of this lemma is that this must be angle phi. And from this point of view, it looks already not that trivial because we don't have clear relation to those angles at the moment. But we probably can do that somehow. Of course, we may do the translation to the point C, and that will make some sense. Just the picture here is already like sort of crowded, messed. But in order to keep that things geometrical, we probably should do that, like to do the angles. Now, actually, what I want to do, I really want to keep this for you to complete at home. So here it will be already looking like angle chasing. So probably by just drawing some parallelograms here and drawing the equal angles here in these triangles, that must be perfectly doable. So that is not mysterious fact. It's quite simple fact. But what I was saying that it's not intuitive is that intuition pushes us here to some fake way that the statement itself here is quite obvious. But it's not obvious because even to understand where we should look for this angle phi, it's something counterintuitive here. So something which we don't imagine when we read this. So here the statement is intuitive just because we have equality of the angles. If by some reasons we would have here phi over 2, then it would be not less and not more intuitive than as this formulation. So for me, that's not intuitive. Like I don't understand from the very beginning why it should be true or not true that this angle, new angle here, should be equal to phi over 2, or not equal to phi over 2, or equal or not equal to phi. For example, pi minus phi, right? Maybe it's a more reasonable version or like some other thing. So here we need to do the exact counting, exact understanding why in these different triangles, like they would be related in this form. And prove that strictly geometrically without intuitive approach, right? Just by counting the angles. And okay, when we do that, when we do this lemma, we will actually find very nice approach to the theorem that we have control over the length of the segments, and also we have control under the direction of the vectors. So that will allow us to deal with the composition of rotations. And finally, composition of rotational homotheties. So by composition of no, sorry. First, just rotational homotheity. No, like, sorry. The topic would be this, but first, what is rotational homotheity? It's oftentimes denotes like homotheity with the center C, coefficient K, and angle phi. So we just take them all together. That would be composition of homotheity with the center C and coefficient K, and rotation at the center C, the same center, and angle phi, which is technically I read it incorrectly because it would be first rotation, then homotheity, and actually there is no difference in that. So we can see and we can prove easily that these two things, they will commute as soon as they have the same center. So we can change the order here. Then some basic properties. First, rotational homotheity is a similarity transformation. With similarity coefficient magnitude of K. So here K is also like, normally K is considered to be equal not zero. As well as sorry. Yeah. So first it's similarity. Second, it changes directions by angle phi. So not just like in the rotations, changes the directions by angle phi, as in rotations. Take. I will give problems to the home task, which will be rotated to this. Which will be sorry. I will give some problems to the home task, which will be related to this topic, of course, so that you study on the cases, on the examples. Because here, of course, we can go to an arbitrary deepness of theory. The question is in the applications. And I tell you these things just because this is really something which is used and which promotes your understanding and intuition by far, actually, if you didn't use it before. Like also practicing this may be almost infinite. But there are several corner examples which would be found in different situations. I find them approachable both and promoting. So that is why I tried to take such large piece of theory today. So very last note, the very last theorem, which is the corner theorem probably, about composition of three rotational homotheties. Composition of three rotational homotheties. With K1 times K2 times K3 equal to 1, and here will be phi1 plus phi2 plus phi3 equals to n times double pi with integer n is either a parallel translation or if image of some point x is not coinciding with x, or an identity transformation ID if there is how it's called I will call it constant point, but there is the clever title for that, the point which is not moved. Sorry, just flew away. So the phi1 plus phi2 plus phi3 times pi. So this turns out to be quite powerful statement. So if we have three homotheties such that the coefficients are adjusted so that in the product they produce 1, and the sum of the angles equals to double pi or 0 or minus double pi, or by some reasons 4 times pi, it will be and if the composition has this constant point, stationary point, then it would be actually identity transformation, or identical. So it will change nothing. Everything will stay on its places. But normally when we apply this to some point, like for finding the stationary point, we keep track of some like clear point, a point which is clear how it moves. And for others, the trajectory would be quite twisted. And by this statement, by this theorem, we'll be able to give very clear location of that point after three movements, after three transformations. So you will see there are very beautiful examples, and there were actually problems from IMO related to this problem. One of the problems, like not recent one though. It was done just by this theorem itself, and that's it. Yeah, so that's it for now. Any questions, comments? Fixed point, yes, fixed point. Right. Yeah, so we finish like by the schedule we finish, and like by the sense we finish. Much theory, lack of practice as for now. So you will have a set of problems related to these things from different sides, from different points of view. Yeah, there is also a comment from Taksin that rational homotheity is also called spiral similarity. Okay, if no questions, no comments, then like still all the time we are online, so like keep sending me questions, solutions, and like wait for some time to get these problems. Hopefully I will do that within today and probably tomorrow.